Welcome! In this session, we will dive into a coding problem titled Valid Word Abbreviation. This problem will test your understanding of string manipulation and logical reasoning. Let's explore the key concepts and approaches to solve it effectively. In this problem, you are given two strings, word and ABBR. Your task is to determine if the string ABBR is a valid abbreviation of word. Now, what does it mean for an abbreviation to be valid? A valid abbreviation is formed by replacing some of the characters in word with numbers. These numbers indicate the count of characters being replaced. For example, in ABBR, the number 3 would mean that 3 characters of word are skipped. There are a few rules to keep in mind here. First, numbers in ABBR must represent at least one character, so they cannot start with 0. Second, any non-numeric character in ABBR must match the corresponding character in word. And finally, consecutive numeric digits in ABBR are treated as a single number. The input constraints ensure that word and ABBR are non-empty, and the length of ABBR will never exceed the length of word. The output is a Boolean value, true if ABBR is a valid abbreviation of word, and false otherwise. Let's look at the first example to understand these rules better. Here, the word is internationalization and the ABBR is I-12 is for N. The output is true because the abbreviation is valid. Breaking it down, the first character I in ABBR matches the first character of word. The number 12 then skips the next 12 characters in word, which are internationally, leaving us with Sation. The next character Z in ABBR matches the corresponding character in word. Then, the number 4 skips the next 4 characters, ASHO, leaving N. Finally, the last character N in ABBR matches the last character of word. Since all parts of ABBR align correctly with word, the result is true. This example demonstrates how numbers in ABBR can be used to skip multiple characters in word. Now consider the second example, where the word is apple and the ABBR is A2E. Here, the output is false because the abbreviation is invalid. Let's break it down. The first character A in ABBR matches the first character of word. The number 2 then skips the next 2 characters, PP, leaving Lu in word. However, the next character E in ABBR does not match the next character L in word. Because of this mismatch, the abbreviation is not valid, and the output is false. This highlights the importance of ensuring that non-numeric characters in ABBR match exactly with the corresponding characters in word. In the next example, the word is substitution and the ABBR is S10N. The output here is true because the abbreviation is valid. The first character S in ABBR matches the first character of word. The number 10 then skips the next 10 characters in word, which are substitutio, leaving N. The last character N in ABBR matches the last character of word. Since the abbreviation aligns perfectly with the structure of the word, the result is true. However, in another example with the same word, substitution, and a different ABBR, S010N, the output is false. This is because numbers in ABBR cannot start with 0. The sequence 010 is not a valid number, so the abbreviation is invalid, resulting in false. This example emphasizes the rule that numbers in ABBR must be positive and cannot include leading zeros. Finally, let's look at the example where the word is word and the ABBR is W2D. The output is true because this abbreviation is valid as well. The first character W in ABBR matches the first character of word. The number 2 skips the next 2 characters in word, which are OR, leaving D. The last character D in ABBR matches the last character of word. As all parts of ABBR conform to the rules and align correctly with word, the result is true. These examples show how different abbreviations can be validated based on the rules provided. To summarize, there are a few key constraints and edge cases to consider. First, the length of ABBR must not exceed the length of word, and the expanded form of ABBR must match word exactly. If the total expanded length of ABBR exceeds the length of word, the result is false. Additionally, a valid abbreviation can also be the same as the word itself. For instance, if word is apple and ABBR is also apple, the output would be true. Edge cases include ensuring that numbers in ABBR do not start with 0 and that both word and ABBR are non-empty, which is guaranteed by the problem constraints. By carefully handling these rules and edge cases, you can determine whether any given abbreviation is valid. To determine if the abbreviation, or ABBR, is valid for a given word, we need to simulate the process of abbreviation and verify that ABBR matches the word accurately. Let's explore some potential approaches we could take. First, consider the brute force approach. The intuition here is to directly generate all possible valid abbreviations of the word by replacing substrings with their numeric lengths. Then, we would simply check if ABBR is one of these generated abbreviations. This could be implemented using recursion or backtracking to explore all possible combinations. However, the complexity of this approach grows exponentially with the length of the word, as there are 2 to the power of n possible abbreviations for a word of length n. While this guarantees correctness, it quickly becomes computationally infeasible for larger inputs. The trade-off here is clear. Although conceptually simple, brute force is inefficient and not practical for solving this problem when scalability is a concern. Now, let's focus on a more efficient approach, the two-pointer simulation. Instead of generating abbreviations, we can directly simulate the process of verifying if ABBR matches the word using 2 pointers, one for traversing the word and another for the abbreviation. There are a few key observations to keep in mind. When encountering a digit in ABBR, it represents the number of characters to skip in the word, and consecutive digits should be treated as a single number. Importantly, numbers in ABBR cannot start with 0, as that would make them invalid. When ABBR contains a non-numeric character, it must match the corresponding character in the word. The algorithm involves initializing pointers for both strings, traversing ABBR, parsing numbers when digits are encountered to skip the appropriate characters in the word, and ensuring non-numeric characters align correctly. Finally, both pointers must reach the end of their respective strings simultaneously to confirm a valid match. This approach achieves an optimal time complexity of O, max, n m, where n is the length of the word and m is the length of ABBR. It's efficient, handles all edge cases, and avoids the overhead of generating or storing intermediate results. However, it does require careful implementation to handle parsing numbers and edge cases like invalid inputs. An alternative approach is to use regular expressions to match the abbreviation against the word. The idea here is to convert ABBR into a regex pattern that represents all possible matches. For example, numeric segments in ABBR could be replaced with .number to represent a wildcard match of that specific length. Then, a regex library could be used to check if the word matches this constructed pattern. While this approach is elegant and concise, it does come with trade-offs. Regex compilation and matching can be slower than the direct simulation approach, especially for longer inputs. Additionally, regex-based solutions introduce extra computational overhead and can be harder to debug. Ultimately, the chosen strategy for this problem is the two-pointer simulation approach. It is the most efficient and direct solution, leveraging clear observations about parsing numbers and matching characters. While regex is an alternative, it's less efficient and more complex to implement. The two-pointer method achieves the ideal balance of simplicity, efficiency, and correctness, making it the optimal choice with a time complexity of O, max, n, m. This ensures the solution scales well even for larger inputs. To understand this problem, imagine you are given 2 strings, one is the original word, and the other is its potential abbreviation. Your goal is to figure out whether the abbreviation is valid. A valid abbreviation allows you to replace numeric values in the abbreviation with a corresponding number of characters skipped in the word, ensuring the overall structure still matches. To solve this efficiently, we can use 2 pointers. The first pointer, I, is used to traverse the original word, while the second pointer, J, navigates through the abbreviation. Using pointers is advantageous because it allows us to directly compare characters in both strings without creating additional copies, keeping our algorithm both time and space efficient. Now, let's see how to traverse both strings. We begin by iterating through the abbreviation using the pointer J. For each character, if it's a letter, we verify if it matches the current character in the word at pointer I. If they don't match, we can immediately determine the abbreviation is invalid and return false. On the other hand, if the character in the abbreviation is a digit, we need to interpret it as a number that tells us how many characters to skip in the word. This involves parsing the full numeric value, such as treating 12 as 12, not 1 and 2 separately. It's also important to check that this number does not start with a leading 0, as that would make the abbreviation invalid. Once we have the number, we increment the pointer I in the word by that value to skip the corresponding characters. Finally, we move pointer j forward to the next character in the abbreviation that isn't part of the current number. After processing all the characters in the abbreviation, we need to validate the boundary conditions. Specifically, we must ensure that both pointers have reached the end of their respective strings. If pointer I has not reached the end of the word, it means there are unmatched characters in the word, so we return false. Similarly, if pointer j hasn't reached the end of the abbreviation, it means there are extra characters in the abbreviation, making it invalid. Key insights to keep in mind include how numeric values in the abbreviation are used to skip characters in the word. Parsing these numbers carefully is critical, especially when handling multi-digit values or ensuring there are no leading zeros. Edge cases to watch for include numeric values that attempt to skip beyond the word's length or abbreviations containing invalid characters like special symbols. Additionally, if the word is empty, the abbreviation must also be empty or contain only valid numeric values. Now, let's analyze the complexity. The time complexity of this algorithm is O, n plus m, where n is the length of the word and m is the length of the abbreviation. This is because we process each character in both strings exactly once. The space complexity is O(1), as we only use a few pointers and variables, without allocating additional data structures. To see the algorithm in action, consider the example where the word is international and the abbreviation is I12L. We start by comparing the first characters, I in both strings, which match. Then we parse the number 12 and skip 12 characters in the word. Finally, we compare the last characters, L, which also match. Both pointers reach the end, so we return true. In another example, with the word apple and abbreviation A2E, we again find a match for a, skip 2 characters based on the digit 2, but encounter a mismatch between L in the word and E in the abbreviation. This mismatch means the abbreviation is invalid, so we return false. This Python implementation solves LeetCode problem number 408, valid word abbreviation. The goal is to determine whether a given abbreviation ABBR is valid for a given word. The approach uses a two-pointer technique, one pointer, I, for word and another pointer, J, for ABBR. First, we initialize I and J to 0. These pointers traverse through word and ABBR respectively. The algorithm processes each character of ABBR to determine whether it matches the corresponding part of word. If the current character in ABBR is a digit, we check for invalid leading zeros. If there are none, we calculate the numeric value represented by consecutive digits in ABBR. This value indicates the number of characters to skip in word. We increment pointer j through the digits and move pointer I forward by the calculated numeric value. If the current character in ABBR is not a digit, we compare it directly with the current character in word. If they do not match, the abbreviation is invalid, and we return false. Otherwise, we increment both pointers to continue the comparison. The loop continues until we have processed both strings completely. After the loop, the function checks whether both pointers have reached the end of their respective strings. If either pointer has not, the abbreviation is invalid, and the function returns false. Otherwise, it returns true. This implementation handles edge cases, such as leading zeros in the abbreviation, mismatched string lengths, and invalid characters. The algorithm runs in O, n plus m, time complexity, where n is the length of word and m is the length of ABBR, making it efficient for this problem. Here, we begin the Java implementation of the valid word abbreviation problem by defining the valid word abbreviation method, which takes two inputs, word and ABBR. We initialize two pointers, I and j, to 0. These pointers will traverse the word and ABBR strings, respectively. We also store the lengths of word and ABBR for easier access. Inside the while loop, which continues as long as both pointers are within their respective bounds, we first check if the current character in ABBR is a digit. If it is, we ensure it's not a leading zero, as leading zeros in abbreviations are considered invalid. Then, we calculate the numeric value represented by consecutive digits in ABBR. This value, stored in number, determines how many characters we skip in word. After processing the digits, we move the pointer j forward and increment I by the value of number. If the current character in ABBR is not a digit, we directly compare it with the corresponding character in word. If they don't match, or if I exceeds the length of word, we return false. If they match, we simply increment both pointers to continue processing the next characters. Finally, we return the result of the condition I equals word length and j equals ABBR length. This ensures that we have processed both the word and the ABBR entirely, with no extra characters left unaccounted for in either string. If both pointers have reached the end of their respective strings, it means the abbreviation is valid. Otherwise, the abbreviation is invalid, and we return false. This implementation efficiently handles the logic for abbreviations by iterating through both strings while adhering to the rules for valid abbreviations. To solve the problem valid word abbreviation, we need to determine whether a given abbreviation is valid for the provided word. A valid abbreviation works by replacing one or more consecutive characters in the word with a number indicating their count. However, any abbreviation that includes leading zeros is immediately deemed invalid. Looking at the first example, the word is international, and the abbreviation is I12L. We initialize two pointers, I for the word and j for the abbreviation, both starting at 0. The first characters, I from the abbreviation and I from the word, match, so we increment both pointers to move forward. Next, we encounter the digit 1 in the abbreviation. By parsing the digits 1 and 2, we derive the number 12. This number tells us to skip 12 characters in the word, updating the pointer for the word accordingly. After skipping, we compare the next characters, L from the abbreviation and L from the word. They match, so we increment the pointers again. At this point, both pointers have reached the end of their respective strings, meaning the abbreviation is valid, and we return true. Now let's consider two examples where the abbreviation is invalid. In the first case, the word is apple, and the abbreviation is A0E. We begin by comparing the first characters, A from the abbreviation and A from the word, which match. We increment both pointers. However, the next character in the abbreviation is 0, which is a digit. Since leading zeros are not allowed in abbreviations, we immediately return false without any further checks. In another example, the word is hello, and the abbreviation is H2O. Starting again, the first characters H from both strings match, so we increment the pointers. The next character in the abbreviation is 2, which is parsed into the number 2. This instructs us to skip 2 characters in the word, updating the word pointer accordingly. After skipping, the word pointer now points to L, while the abbreviation pointer points to O. These characters do not match, so we return false. This illustrates how mismatches or invalid patterns in the abbreviation lead to a failure. There are a few key details to note about this algorithm. First, it specifically checks for leading zeros in the abbreviation. If it encounters a 0 as part of a number, it immediately returns false, ensuring that such cases are handled correctly. The two-pointer approach, with I traversing the word and j traversing the abbreviation, ensures the algorithm processes the strings efficiently. By carefully matching characters and skipping the appropriate number of characters whenever a digit is parsed, the algorithm maintains correctness. Regarding complexity, the time complexity is O, n plus m, where n is the length of the word and m is the length of the abbreviation. This is because we process each character or digit exactly once. The space complexity is O1, as the algorithm uses only the 2 pointers and does not rely on any additional data structures. To analyze the time complexity of the solution, we need to consider the traversal of both the abbreviation string ABBR and the word string word. First, the algorithm iterates through each character of ABBR exactly once. This contributes O(m), where m is the length of ABBR. If a numeric sequence is encountered, a while loop processes all contiguous digits. Importantly, the total cost of processing these digits across all iterations is still O(m), because each character is visited only once. Similarly, the pointer I moves across the word string based on the numeric values in ABBR or when characters match. This traversal is bounded by the length of word, contributing O(n), where n is the length of word. Lastly, each individual operation within the loop, such as comparisons or arithmetic calculations, is performed in constant time, O(1). These operations don't affect the overall complexity, as they scale linearly with the traversal. Therefore, the key contributors to time complexity are the lengths of ABBR and word. When we combine these factors, the overall time complexity of the solution becomes O, max, n and m, where n is the length of word and m is the length of ABBR. This accounts for the fact that the algorithm processes both inputs in a single pass, but only the longer of the two determines the dominant term. Moving on to space complexity, the primary contributors are the pointer variables I and j, which are used to traverse word and ABBR. These variables require only O1 constant space. Additionally, there's a temporary variable number used to store numeric values when parsing digits in ABBR, which also consumes O1 space. Since the input strings word and ABBR are provided and neither duplicated nor modified, they don't add to the space complexity. Thus, the space complexity of the solution is O1, as no additional memory usage scales with the size of the inputs. To understand the efficiency gains of this approach, let's compare it to a brute force solution. A naive approach would involve generating all possible abbreviations of word and comparing each with ABBR. Since there are 2 to the power of n possible abbreviations for a word of length n, this has an exponential time complexity of O2 to the power of n. Additionally, the process of comparing each abbreviation with ABBR adds further computational overhead, making such an approach impractical for large inputs. In contrast, the optimized solution directly validates ABBR against word in a single pass, reducing the time complexity to O, max, n, m, and the space complexity to O1. This makes the approach far more efficient. Looking at different scenarios, the best-case scenario occurs when there's an early mismatch in ABBR and word, allowing the algorithm to terminate in O1 time. On average, the algorithm processes most of ABBR and word, taking O, max, n, m. In the worst case, the algorithm processes both inputs entirely without early termination, which also takes O, max, n, m. Finally, let's solidify our understanding of the time complexity with a simple mathematical proof. Since each character in ABBR and word is processed at most once during the traversal, the total number of operations performed is directly proportional to the sum of their lengths. This means that the time complexity is O, max, n, m, as the algorithm scales with the larger of the two inputs. For space complexity, no additional memory is allocated that grows with the input size. The algorithm uses only a fixed amount of space for pointers and temporary variables, resulting in a constant space complexity of O1. This combination of linear time complexity and constant space complexity makes the solution both scalable and efficient, even for large inputs. When solving the valid word abbreviation problem, there are several common mistakes to watch out for. First, misinterpreting numeric abbreviations is a frequent error. Remember, when you see a number in the abbreviation, it represents the number of characters to skip in the word, not individual digits. For instance, in the abbreviation W12D, it means to skip 12 characters, not treat 1 and 2 separately. Misunderstanding this can lead to incorrect results. Another common mistake is skipping edge cases. For example, scenarios like an empty string for the word or an abbreviation with invalid formats, such as W03D, must be handled. These edge cases can cause runtime errors or unexpected outputs if overlooked. Lastly, ignoring leading zeros in numbers is another pitfall. Numbers like 01 foot in abbreviations are invalid and must be rejected. Failing to account for this could result in accepting incorrect abbreviations, so it's crucial to validate your inputs carefully. Another important point is ensuring that both the word and abbreviation are fully matched. Stopping the comparison too early or assuming partial matches are valid can lead to errors. For example, if the word is word and the abbreviation is war, the result should be false because the abbreviation doesn't fully match the word. Additionally, incorrect pointer updates can be a source of bugs. When processing numbers or characters in the abbreviation, the pointers for both the word and abbreviation need to be updated correctly. If the pointer jumps are miscalculated, you might skip or overlap characters, leading to inaccurate comparisons. Properly managing pointer updates ensures that the process stays in sync and produces the correct results. To approach this problem effectively, focus on simulating the abbreviation process step by step using 2 pointers, one for the word and one for the abbreviation. The key is to identify patterns, such as how numbers in the abbreviation indicate how many characters to skip in the word. It's essential to extract these multi-digit numbers correctly to ensure accuracy. From a complexity perspective, an optimal solution should have a time complexity of O, n plus m, where n and m are the lengths of the word and abbreviation, respectively. During interviews, it's also helpful to clarify edge cases with the interviewer, such as handling leading zeros or empty strings. This avoids assumptions and demonstrates thoroughness in your approach. Additionally, understanding similar problems can provide valuable insights and strengthen your problem-solving strategy. Speaking of similar problems, there are a few on LeetCode that share concepts with valid word abbreviation. First, there's LeetCode 186, Reverse Words in a String 2, which also involves pointer-based string manipulation. Then, we have LeetCode 844, Backspace String Compare, which uses a two-pointer technique to validate string transformations, just like this problem. Another related problem is LeetCode 161, One Edit Distance, which involves comparing strings with specific constraints. Each of these problems can help you refine your understanding of pointer-based techniques and string manipulation, making you better prepared for variations of this challenge. Finally, let's discuss some alternative approaches to solving this problem. One option is a recursive approach, where you process the abbreviation step by step, either skipping characters for numbers or matching characters directly. While this method is easier to implement for small inputs, it risks stack overflow with large inputs due to deep recursion. A more efficient method is the iterative approach, which uses two pointers to traverse the word and abbreviation. This approach avoids the recursion overhead and handles large inputs well, though it may require more careful implementation. Lastly, there's the regex-based approach, where the abbreviation is converted into a regex pattern and matched against the word. While this method is elegant and concise, it tends to be less efficient and can struggle with edge cases. Each of these approaches has its trade-offs, so it's important to choose the one that best balances simplicity and efficiency for the given problem. Great job! To wrap up, we summarized the key points of solving the valid word abbreviation problem. Remember to practice similar problems to reinforce your understanding. Thanks for watching, and don't forget to stay tuned for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!